All right, welcome to coronavirus video number 3. Let's do some problem solving. So this first problem is going to ask us what is happening to object 1. I'm going to go ahead and label these 1, 2, and 3 from the gravitational interactions between these objects. And so we've got an F12 going this way and an F13 going that way. And so really all we have to do is just calculate each. And so we're going to start with F12. And by the way, if you recall, Newton's law of universal gravitation is equal to big G, mass 1, mass 2, divided by the distance squared between them. And so we're going to go ahead and do those calculations for the first one. And so what do we get? We get G M1, M2 divided by the distance R12 squared. And so if you look at the coordinates that are on this, right, we got 3, 1, and this guy, of course, is at the origin. If we draw ourselves a little triangle, right, what do we get? We get 3 this way and 1 this way. So this right here is going to be radical 10 using Pythagorean theorem. And so our F12 will be equal to G, we're going to go ahead and plug some numbers in. 25 times 40, nope, not 45. That would be the other one. Times 35 divided by the distance between them squared, which would be 10 because it's radical 10 squared. And so if you do some math there, what do we get? We get G times 2.5 times 35, which would be equal to 70 plus another half of 35 plus 17.5 G. Hopefully I got that math right. And so my F12 is equal to 87.5 G. And so I'm going to go ahead and box that one. And then we're going to go ahead and move on to F13. So F13 is going to look very similar. And so it's going to be M1 and M3, and then R13 squared. All right, and that particular triangle, that R13, is going to have a 3, 4, 5 triangle going on it, because it's going to be this distance made by that triangle right there. And so what do we get? We get F13 is equal to big G times M1, which is 25, times M3, which is 45, divided by R13 squared, which is 5 squared, or 25. Therefore, these two guys cancel out, and so we're left with 45G. Okay, so these are the two, these are going to be the two forces acting on them, but now we need to figure out, all right, what about the net force acting? And so what we need to do now is we need to break these forces into the components. And so we're going to have an F12 and an F13. We're going to have an X component and we're going to have a Y component, right? Okay, so what was F12? F12 was equal to 87.5 G. And F13 was equal to 45 G. Okay, and so for this guy, F12 was going at an angle of what? It was 3 and then 1, and so the angle would be the inverse tan of 1 over 3. And so then we would have to figure out the x component of that, which would be simply the sine of that, right? So let's go ahead and let's figure out what the tan of that is, the inverse tan. Let's go ahead and get the calculator out here. So, all right, what do we have? We need some trig on there too, don't we? We do. Where's my trig? 1 divided by 3 is equal to, and then there's my trig. Let's do the inverse tan of that. And so what do we get? We get theta. Oops. Get theta equal to, what was it? It was 71.6. So theta is equal to 71.6 degrees for that does not look right. It is not. Let's try this again. 1 divided by 3. 3 is equal to trigonometry. Second. Inverse tan. That looks something much more reasonable. It's annoying every time I come off of that. It moves my pen. All right, so we get 18.4. So let's go ahead and erase this. We're at 18.4 degrees. That makes a lot more sense. Okay, so there's our first one. 1, 2. And then this guy is going to be what? This was inverse tan of which one was it? It was 4 up. And so it would be inverse of 4 over 3. And so for that guy, what do we get? Bring our calculator up again. And so we get 4 divided by 3 is equal to, and then I'm going to take the trig second inverse tan, and we get 50. Do that every time, don't I? So it was 53.1 degrees. Okay. And so you can kind of see what we're going to do here now, guys. We know that F12 is acting up and to the right. And so it's going to be 87.5 G positive. So it would be sine of 18.4 degrees. Okay. And then our Y component would be 87.5 G cosine of 18.4. Actually, I flipped those, didn't I? This right here would be my cosine. This would be my sine. All right. Now for the other guy, and then we'll stop there. We've got 45G. And this one's going to be negative at the beginning because it's acting to the left. For the x component, it'll be negative, and it'll be cosine of 53.1. And then this one will be positive because it's going up, and it will be 45G sine of 53.1. If you add all that mess together, you will get the sum of your forces. But I will leave that to you because that's just a bunch of arithmetic. All right, let's move on to our second example problem. And so our second example problem is going to be a binary star system. It's actually pretty neato. Binary star systems exist a lot in our universe. And so what we've got here, we actually have a star in mass number 1 and quote unquote a black hole at mass number 2, and they are orbiting each other. Okay, and they're orbiting each other, and this is kind of the definition of a binary system, is that they are have angular velocities that are matched, and so they rotate around each other at exactly the same angular velocity, and so they're in lockstep. Like I said, it's pretty neat. Okay, and so the question is, how are mass 1, mass 2, and radius 1 and radius 2 related to each other? Well, ladies and gentlemen, we know that we've got gravitation and we have circular motion. And so we can say for both of them, our centripetal acceleration will be equal to my gravitation. All right, and so for number 1, so we'll call him body 1, we know that my FC1 will be equal to my FG1. Okay? And so what's FC equal to? Well, FC for this first guy is simply mv squared over R1, right? And that's going to be equal to my gravitation, which is going to be m1, my gravitational force between the two, divided by 1 plus 2 squared, that radius. All right? Okay. Let's do some magic now. All right? So now we're going to go ahead and we're going to move on to body number 2. And we'll come back to this guy. So body 2 is similarly going to have the centripetal acceleration equal to the gravitational force between the two, which is, by the way, going to be the same. Okay, but our centripetal acceleration is going to be a tiny bit different here. Right, so because this guy, the second one is orbiting in the shorter radius, right? This R2, whereas the R1 was the first mass was orbiting at a little bit further away. And so we know that that is going to be equal to G m1 m2 over R1 plus R2 squared. Okay, and why did I say R1 plus R2? Is because it's the actual total distance which causes the gravitation. And so no matter where that pair is, that distance will always be R1 plus R2. Okay. All right, now what we're going to do is we're going to do a little bit of, apologies, this was M2. And this guy right here was M1. All right, now we're just going to do a tiny bit of algebra here, some algebra magic here. You ready? Okay, let's go red. I'm going to multiply both sides by R1 over R1. Okay? And so what's going to happen? So what I'm going to get now, and I'll do the same thing for this one, except on this one, I'm going to do R2 over R2. And this is a trick. Okay, and so what do we get? We get M1 R1 V1 squared over R1 squared will be equal to G M1 M2 over R1 plus R2 squared R1 over R1. Okay? We're going to do the same thing for this guy over. Well, let's do some canceling here, right? So this guy and this guy are going to cancel out. And so we basically get, let's go ahead and, you know what, let's do the other guy first. And then you'll see how this all comes together. Okay, and so for this guy, the analogous, right, and I'm not going to go through all the steps, right, but it's going to be what? It's going to be M2 V2 squared over R2 squared will be equal to G M1 M2 over R1 plus R2 squared over R2 in this case. All right? Okay, now here is where it's sneaky, sneaky. All right, you ready for the sneaky, sneaky? Sneaky, sneaky snake. We know that this is a binary system, therefore the angular velocities are the same. Guess what? This right here, and this right here are the same. Okay? And so I can basically now set these two equal to each other. And or I can actually know what I'm going to do. I'm going to divide them out. I'm going to do it the sneaky, sneaky way. Okay? So V1 squared over R1 squared over M2 V2 squared over R2 squared will be equal to all these crazy G, M1, M2, but you'll notice that they're going to be the same. Plus R2 squared, and he's going to be over R1 divided by G, M1, M2 over all this mess. Keep wanting to do that. I keep wanting to square the first one. Just the combined distance, right? Times R over R1 over R2. And so what you notice, ladies and gentlemen, is all this cancels out. These two cancel out. And so what do we get? We get M1, the ratio of M1 to M2 will be equal to, will be equal to R2 over R1. And so, ladies and gentlemen, there is your answer. And so the mass of the interior, so if I just solve for this, okay, if I just solve for this, the mass of the interior sun will be equal to what? It'll be equal to R1 divided by R2 times M1. And since R1, this guy right here, is always going to be greater than your R2, because the R1 is outside the radius, the mass of this guy always has to be bigger than the mass of your M1. All right, ladies and gentlemen, let's go ahead and do the last sample problem here, example problem. What we're going to do now is we're going to calculate our escape velocities from Earth, Mars, and Jupiter. Now, we did this in the notes, but we can just derive it really quickly. And so the question is that's asked is, what is the necessary velocity so that an object can completely leave, infinitely away, can completely leave the gravitational effects of a planet? And so if we start at the instant right after the object gets its velocity, we know that delta E will be equal to 0. And so what delta E's or what kinds of energies do we have? Well, we have our delta K's, and our delta U's, which is pretty much all we have with gravitation, will be equal to 0. And so we have my K final minus my K initial plus my U final minus my U initial will be equal to 0. Well, the very definition of escape velocity is the minimum velocity required so that at the final state, it kind of just barely comes to a stop, infinitely away from the planet. Okay, and so my final will be zero because I know that my U is what? My U is equal to negative G mm over R. Okay? All right, so let's do this. And so we know those two are 0. And so we know that our K initial will be equal to negative U initial. And so I've got 1/2 mv squared will be equal to G m big M little m over R. And so what's that come out to be? That comes out to be my velocity will be equal to radical, because my m's will cancel out, my little m's, will be equal to 2 times big G big M divided by the radius. And so we can use this formula. So this is my escape velocity, which I derived for you again, to do each of these. And so let's do the Earth first. And so velocity is escape velocity from the Earth would be what? It would be radical 2g, and in this case, my m is what? It is 5.97 times 10 to the 24th. And my radius of my Earth is what? It is 6.4 times 10 to the 6th meters. So that would give my escape velocity for Earth. I will calculate it at the end. Then we've got a velocity from Mars. We're going to plug in 2g, instead of 6 times 10 to the 24th, we get 0.64 times 10 to the 24th. And so Mars is like a tenth the gravity, or sorry, the mass of Earth. It's crazy, isn't it? And then the radius of Mars is 3.4 times 10 to the 6. All right, okay, getting there. And then lastly, escape velocity for Jupiter is what? It's radical 2g. And my mass, it's super massive. Jupiter is huge. It's almost a star. Times 10 to the 24th. And so you can see that relative to Earth, right? Earth is 6 times 10 to the 24th. Jupiter is 1900 times 10 to the 24th. So it is super massive compared to Earth. And then the radius is also rather large, 69.9 times 10 to the 6 for my radius. Okay, I'm going to go ahead and calculate each of these and see what our escape velocity. All right, let's see what we came up with in our calculator. So for the escape velocity of Earth, we've got 11,155 meters per second. For Mars, we have 5,011 meters per second. And for Jupiter, we have a whopping 60,184 meters per second. And so you can see much harder to escape Jupiter than it is Earth, and it's much easier, although not as easy as it appears at first glance for how big Mars is. So it's about half of what the escape velocity of Earth is. So there you go.